Swayam Prabha. Digital India. Educated India.
So, we had an idea of what is meant by long term performance prediction. We said that the meteorological cycle repeats itself over an year. Academic analysis also is based upon the cost benefit analysis over a year, over the lifetime of any system in particular. We identified the difficulties with the solar energy systems, namely the you can't get the performance output as simple efficiency multiplied by the solar radiation falling over a long period of year for several reasons which we have listed. And the methods that are available to us are conducting system scale experiments, which could be time taking and of course, also expensive, and the effect of parameters cannot be easily studied, because if you do an experiment for 1 year with one slope and if you want to change it for another slope, you need another year of study to get that performed. So, simulations turn out to be via media, that means you mimic the solar cycle and you model each component, knit together those models and give the output of the first module to the as input to the next module, like for example, a solar collector dumping useful energy into the solar tank where the temperature increases, which goes to meet the load. So, we can develop models for the number of types of components, and these things have proved to be effective, which will take a fraction of time, it does not require an year. And these simulations basically depict the system into several components and employ models to describe each component performance. The components are coupled with appropriate linking modules. So, this requires a detailed meteorological database. One is availability of the data and the ready availability of the data. So, for example, if you consider the Indian meteorological stations, monthly averages are there available even on the net, but if you want hour by hour data, one has to acquire from the meteorological station or office in the Pune, and then all these numbers may have to be converted into a tape or put in the computer program to get that, which is a laborious task. But however, if it is done once, it can be used. The other thing is, most of these meteorological stations are at the metros or the cities. It is very likely, because of the premium of the land, solar energy systems are likely to be installed at smaller places, maybe villages, where the actual data collection did not take place. So, in the long run, we might say, though simulations are cheaper, it requires the skill of experts or to stitch together the component models, and it requires of course a detailed database. Transys is one such program which was developed at the University of Wisconsin Madison, and then SimShack is another. This is due to WIN, though it does not contain as many components or modules as Transys. Solcast is a simplified method relatively. It simulates a bright day and a cloudy day, and attaches certain weightages to get an overall performance. So, one can look at the textbooks by Duffy and Beckman, and or this program can be downloaded, a limited version free, and 40 examples have been given. One can, who is interested in going through those things, go through those things and obtain the performance of the certain standard systems. So, that gives you a feel how the data is, meteorological data is used and how the components are put together. So, in one sense, You may say the somewhat disadvantages are you need detailed data, skill of experts and computational power. So, people have tried to lessen the computational requirement by using a reduced data set or even at times resorting to synthetic data. Basically, synthetic data mimics the meteorology of the particular location, though it may not exactly satisfy hour to hour, day to day, but in general it will reproduce the averages which are good enough to get a performance monthly wise or yearly wise. This leads to an advantage. Almost all the data can be generated through sort of equations, though your component models could be analytical, which can be clubbed together along with this data. In other words, if I try to give an example, delta equal to 23.45 something, this equation is much more amenable for computer implementation than a set of 365 values of data delta for each day. Now, so if you consider, you will also notice many of the systems are standard systems. Like say for example, most commonly used could be a domestic hot water or space heating or a combined domestic hot water and space heating or a simple process hot water. For example, if you consider silk industry, the cocoons are put in a boiling water at a water of temperature of about 80 degrees, 85 degrees. Degreasing is done around 80, 85 degrees. So, there are a number of applications where hot water is required at a given temperature. So, these are the some terminologies which have become more common in the US, which when we translate to Indian conditions, which I shall point out slight differences, one has to be a little careful. For example, space heating T above 20 degrees C is acceptable. Generally, the comfort condition is approximately 20 degrees centigrade in the room. So, any energy that is available to at or above 20 degrees centigrade is useful and you can utilize for the purpose of space heating. Similarly, this domestic hot water, although you may be taking bath at a higher temperature and washing the dishes also may be at a higher temperature, above 20 is also useful. For example, if your ambient temperature or the mains temperature is much lower than 20, like 10 degrees, 11 degrees, even to wash your hands or whatever, and you need 20 degrees is a comfortable condition. So, particularly in cold countries, there is a lot of application, a lot of water needs to be heated from the main supply temperature, which is typically 11 degrees in the US to 20 degrees or above. The methods whatever we are going to talk, it does not mean they supply only at 20, they may be supplying at more than 20, but for the meeting the load it is not acceptable to have anything less than 20. Since there are large number of applications of the standard systems, people have come out with what are called design methods. Simulations, they do serve their role whenever you want to design a large system, an unconventional system. And typically large systems, say for example, you go for a power generation or solar furnace, solar desalination. Every specific detail of that particular location has to be taken into account, and the investments may be of the order of few crores, and simulations cost is worth it. But if you want 60 liters of water at 60 degrees C, a domestic water heating system for bathing, possibly the simulation cost may remain the same, but the system cost will be only a fraction of the power generating system. So, simulations are not that much welcome, and one goes for the standard design method. This is also has been the need of the industry to have a simplified method without calling for the skill of experts. So, some of the resulting methods are popularly referred to as, one is the F chart method, again developed at the University of Wisconsin, Madison, and the other one is phi bar F chart method. So, I have given the references. These methods make 12 monthly calculations. As we have discussed at length, for the solar energy systems, or the solar load fraction is the performance indicator, and if F is the monthly solar load fraction Fi, and load Li is the load fraction, load on the system for a month I 1 to 12, this is the yearly solar load fraction. So, this F chart and phi bar F chart method will essentially give you F, the monthly solar load fraction. We have also discussed earlier that if the energy supplied by the solar energy system is in excess of the load, that is not taken into account. So, F is always less than or equal to 1. Now, what is the difference between these two methods? If you have F chart method, applicable if energy supply greater than or equal to 20 degree centigrade is accepted. So, again contenders could be domestic hot water and space heating and a few other such applications which require accept 20 degrees C. And then the in phi bar F chart, phi bar comma F chart, specify T minimum. In other words, you can specify we want the energy delivery at or above a particular temperature, 60 degrees, 50 degrees, 80 degrees, whatever it is. In other words, T minimum may be 60 or 80, etc. So, now since you are imposing that the energy delivery should be above a particular level, my critical radiation level comes into the picture. For example, if this is this typical solar radiation distribution IT on the solar collector, this is critical radiation level corresponding to a T minimum of 50. This will be corresponding to a T minimum of 60. So, if you want energy delivery at or above 60 degrees centigrade, this part of the solar radiation is useful, whereas if it is at 50, this also is useful. So, consequently, we shall find out what is the radiation available to you above the critical level over a month, and that will be signified or indicated by the so called phi bar, which stands for the monthly average daily utilizability. We will spend some considerable time in how to calculate this utilizability and what is the significance. At this stage, I am pointing out the F chart and phi bar F chart method differ because you specify a T minimum. All the solar radiation available corresponding to a particular level is not useful. It will depend upon the T minimum that you wanted. Higher the T minimum, lower will be the utilizability, and hence my useful energy supplied at that temperature or above the temperature, which constitutes a lower or higher solar load fraction. So, that is why F chart method is modified with phi bar and called phi bar F chart method. Now, if you look at it, what are the applicability? These correlations, first of all, they calculate monthly solar load fraction. So, day to day how much of load is met, it cannot give. And they have been developed in terms of certain non-dimensional parameters. There are minor variations between F chart and phi bar F chart for some reasons. One is the non-dimensional collector loss. Okay. And the other is and non-dimensional absorbed energy. Okay. If this is we call it x, let us say, this we call it y, approximately f should be proportional to x minus y if there are no nonlinearities, provided they are consistently unit wise, scale wise, they are defined. Okay. So, you can expect a term like x minus y plus so on and so forth. Sorry, it should be y minus x. Y is the absorbed energy minus the losses. This is my simple useful energy equation, looks like the absorbed energy minus the loss. But on a monthly scale, because of excess energy, because of other losses, because of pumping, because of controls, so on and so forth, it will not be a simple linear function of y minus x, but it will be a nonlinear function, which we will see. So, that is why I have already explained the additional parameter is the utilizability that appears in the phi bar F chart method, which in a way takes into account at what temperature the energy is delivered. Now, how these methods are or equations are developed? So, you do simulations for a large number of locations. And for collectors over a range of parameter values. For example, if you consider the overall loss coefficient, typically UL may be 4 watts per meter square degree Celsius in for a 2 glass cover, or 8 watts per meter square degree Celsius, right. So, if you somewhat do 2 watts meter square degree C to maybe 10 watts, it will include an extremely good collector and also fairly bad collector. So, that is how these correlations have given. Now, what we mean by standard systems, 4 figures are shown here. For example, you have a collector with a heat exchanger, which dumps through another heat exchanger into the storage. From the storage, it may go to an auxiliary tap, a tank, from which it goes to the tap. So, that forms part of the combined liquid based space and water heating system. And then through the delivery device and another heat exchanger, it goes to the house, which will be meeting the space heating. The auxiliary will come in whenever the solar is insufficient, and either for hot water or space heating. So, it says, of course, suppose I do not have a heat exchanger between the collector and the storage loop, I can put the effectiveness of the heat exchanger as unity, then automatically it takes care of that collector is dumping or delivering energy directly to the storage. If auxiliary tank is not there, there will be no loss, and of course, the delivery will depend upon the temperature that is available in the storage tank. Next one is a typical and similar system, but it is air based. The difficulty with air based system is you cannot store, because the specific heat and mass is smaller product. So, what you do is, or rather it requires a huge volume with losses. So, you store the energy in the so called pebble bed over here, and a pebble bed is nothing but a pit. You can put it underground with about 1 centimeter 1 inch pebbles all packed. So, when there is excess energy, the hot water goes through that, heating the pebbles, and then when there is no solar energy, cold air goes through the pebble bed, picking up the energy that is stored during the charging time. So, third one is a closed loop system. Similarly, auxiliary is put auxiliary heater is put again in series, so that it can make up the deficiency in the temperature or deficiency in the quantity. Fourth one is a service hot water, which again calls for a certain desired temperature. So, F chart method can be modified to take care of a specified temperature that we will see in the LEN. Now, if I try to separate this F chart and phi bar F chart method, so somebody can ask what are the limitations or under what conditions F chart method is applicable. So, at or above 20 degrees C, of course, generally we said that space heating or domestic hot water, also used for service heating with a modification. And it is correlated to two non-dimensional variables, which is a non-dimensional collector loss. So, F is a function of x and y, where x is the non-dimensional collector loss and y is the non-dimensional collector absorbed energy. Okay. And the specific numbers rather form will be the same. Correlation for the air based system and liquid based system differ slightly, and in general air based system means the working fluid in the collector, rather it picks up the useful energy air. I have not yet really I have not seen or heard a gas being used instead of air, except some refrigeration applications. People are trying carbon dioxide, etc. And the liquid based systems, mostly it is water, though antifreeze, glycol, etc. may be used, or a thermionic fluid also can be used, where the thermal capacity characteristics will be better, so that your storage will be less volume wise, etc. And in F chart and phi bar F chart, they assume all the collectors are connected in parallel. so that each collector receives the same inlet temperature, and if the size and everything is same, delivers at the same temperature. Consequently, the performance will be a function of the number of collectors or the area directly proportional. And this is a wide range for which the simulations have been developed, based upon which the correlations have been formulated. First, the material property I can say tau alpha normal 0.6 to 0.9, and this is product of heat removal factor and the area of the collector 120 meter square. So, this appears to be somewhat lower, but possibly assuming the linearities one can go for a higher range also, but strictly speaking they are expected to give acceptable results when they are applied in the ranges that we are specifying, and UL can vary from 2.1 to 8.3 watts per meter square degree C, and slope between 30 degrees less than or equal to beta less than or equal to 90 degrees. So, this seems to be a little limitation if you apply for a tropical climate and let us say something like southern India, and your latitudes will be lower than 30. In fact, most of India is less than 30 degrees. So, this beta may be a limitation, and this will come again. Building heat loss coefficient, so many watts per meter C for degree C. U is the overall loss coefficient if you consider, and A is the surface area of the building. Then U into A will give a product, which when multiplied by my temperature difference outside will give the loss that is taking place from the house. So, from the loss that is taking place from the house, I can calculate what is the space heating load. If the house is going to be kept at a 20 degrees C and the ambient is, let us say, is 13 degrees C. So, Q house loss equal to U A of the house times, let us say, 20 minus T ambient in a simplistic manner, though it may have to be averaged or weighted averaged over a period of time. So, this is nothing but an overall loss coefficient multiplied by the area participating multiplied by 20 minus T A. So, this is a terminology which, if you have got a standard construction of 1 bedroom or 2 bedrooms, you may have a UAH typically from 200 watts per degree C to 600 watts per degree C, depending upon how well it is insulated or how well it is not. So, this is used for calculating the spacing load, and the other symbols like UL, FR, tau alpha normal and beta we are already familiar with. So, this air based systems again there are other variables other than tau alpha, A, FR, UL and beta and UAH. What is the flow rate particularly for air based collectors? In the case of air collectors, my heat transfer coefficient strongly depends upon the air flow rate, number one, and the stratification in the pebble bed may be seriously affected depending upon the flow rate. In other words, you expect a higher temperature air to be at the higher level because of the lower density, and if a gust of air or a blast of air goes through that with a high velocity, this stratification may be disturbed. Consequently, the storage performance will be affected if the flow rate is too high. So, there is a standard flow rate for which the simulations have been made, that is 10 liters per meter squared, is it per hour? Yes, 10 liters per second per meter square of the area. So, you expect that the correlation to be valid if your flow rate is around 10 liters per meter square, 9.9 is fine, and the storage size is 0.25 meter cube per meter square. This is the pebble bed volume. The pit we were showing earlier in the figure. So, you provide a 0.25 meter cube per square meter of area. Now, if you take into account the specific heat of the pebbles roughly 1 inch size and randomly packed, and this may correspond to a heat capacity about 350 kilojoules, which will have something relevant in the case of water heating systems, when once you specify the mass specific heat product of the storage tank, assuming the fluid to be water. So, the solar load fraction for air based systems. So, for the sake of clarity, I will write F subscript air 1.04 y minus 0.065 x minus 0.159 y squared plus 0.00187 x squared minus 0.0095 y cube, where x is the non-dimensional collector loss F r U L times 100 minus T A bar into delta tau times collector area A C by L. So, this will be non-dimensional if L is in joules, U L will be, you can say, joule per second meter square degree centigrade, and delta T will be seconds, area will be meter square, and delta tau sorry, and this temperature difference is again degree C. So, this U L is in this much. So, numerator is joules and denominator also is in joules. Now, what you will find here is the number of seconds in the month is delta tau. AC is area, it is not unexpected that the loss factor should be proportional to the U overall loss coefficient. Of course, this is a non-dimensional factor, the time, area, and 100 minus T A bar. This 100 has nothing to do with boiling point of water, that I think somehow it gives that impression, but just 100 minus T A is to scale x. If I put it as 20 minus T A or whatever is the collector operating temperature minus T A, then we may get a too large a value or too small a value for x. So, it is desirable whenever you have any empirical correlation in general, if the variables are of comparable order of magnitude, your accuracy will be better. If x is something like 0 to 10, y is 0 to 3 or 0 to 4, you will have a better correlation. Instead of y changes from 10 to the power 6 to 10 to the power 9 and x changes from 10 to the power minus 3 to 10 to the power minus 1, the effect of x will be, y will be completely lost, because the scales of those numbers are hugely different from each other. So, that is the non-dimensional collector loss, and I will again make a comment after I define this y, the non-dimensional absorbed energy F r tau alpha bar into H T bar times n into A C upon L. A C is the area, n is the number of days in the month, H T bar is the monthly average daily radiation on the collector surface multiplied by monthly average transmitted absorbed product, of course, multiplied by the collector property heat removal factor upon the load. Now, you will understand all the processing we have done is to get this H t bar, get this tau alpha bar, and of course, in the previous definition of x, u l and f r, right. That means, my collector parameters. So, f r u l and f r tau alpha, and then my tau alpha bar comprising of tau alpha bar beam, tau alpha bar diffuse, tau alpha bar ground. So, all the trouble we have gone through is worth it. It comes into the picture now in calculating my y, and the geometry is related ultimately through f r. So, these are symbols are explained, and L is the load on the system. So, given the collector parameters, I can calculate. Now, the comment I was trying to make was, initially I just said that f should be, because non-dimensional, y minus x. Of course, there are non-linearities x squared and y squared because of the losses, etc. So, the constant associated with y is 1.04 y, pretty close to 1, whereas this is 0.065, approximately 1/16th, which without the benefit of a computer, what I think is 100 minus T A is inflated by a factor of 4, and delta tau is inflated by a factor of 4, because typically if the collector operating period is 6 hours, the losses do not take place from the collector all the 24 hours. Okay. Tank losses may be there, pipe losses may be there, but the collector is shut off. So, there is a sort of overestimate of the collector in terms of the delta tau being 24 hours, and this 100 minus T A may be typically 3 to 4 times the actual whatever is the temperature difference responsible for the losses. So, I have got a factor of 16, that becomes a 1/16, which is fortunately according to my imagination, that almost coincides with 0.065. So, the other things are the nonlinearities. So, at times why I specifically mentioned is it is not just the imagination part of it. You will have a sensible correlation if you can think of what could be the functional form and what type of a relation a particular independent variable, dependent variable may have with the independent variables. So, load in general may consist of space heating load and water heating load and loss from the tank. Water tank, there will be a certain loss taking place. So, that is also a part of the load to be met by the system. Of course, at times this loss may be contributing to heat your room, then we will not take into account. So, we will go one by one how to calculate these things. So, LSH, the simplest way is from auxiliary bills. If it is an already occupied house and has a space heating system, be it gas heated or electric heated or steam heated, one can find out the utility bill and find out so much is the space heating load, or you can estimate LHS as building loss coefficient. This is where my building loss coefficient is coming, multiplied by DD. DD is the degree days, not an official designation. So, this is DD is degree C day. I will explain to you. This is to make it hours, this is to make it seconds, because this UAH is watts per degree C, right. So, that is joule per second degree C multiplied by second, that makes it joules per degree C. So, this is degree C day, day is converted into seconds. If you have an ambient temperature of 13 degrees, let us say, and comfort condition, this is let us say T A. Comfort condition is 20 degrees C. So, this 13 is 20 minus 13, 7 degrees C short. If this lasts for one day, suppose ideally my comfort condition does not change, it is 20 degrees C, throughout the day 13 degrees C is maintained, then this will be having 7 degree days. Okay? If the ambient temperature is 13 and the comfort condition is 20, it is deficit by 7 degrees. So, you have a degree days of 7. Now, of course, this 13 may be varying for 2 hours at 13, 17 for 1 hour, 12 for 3 hours, so on and so forth. So, proportionately you can calculate how many degree days each one. If it is 2 hours at 13, it will be 2 by 24 into 7, 1 hour for 17 is 3 into 1 by 24, so on and so forth, and one can come out with the total number of degree days in the month. That is what we are calculating. So, degree C day is for the month. So, you can calculate from the building loss coefficient and the degree day data and what is the space heating load. Another thumb rule, approximately, if T A bar, let us say monthly average daily ambient temperature, which you can see from the meteorological data in books like A Money for Indian locations, or Duffy and Beckman for US and Canadian locations, or the Ministry of Non-Conventional Energy Sources website these days. If T A bar is let us say 15, then 20 minus 15 is 5 degrees multiplied by 30, that will become 150 DD approximately. If my ambient temperature is 15 degrees for the monthly average, and if 20 degrees is the comfort condition, then 20 minus 15 deficiency is there. So, 150 degree days will be there. Of course, the biggest approximation is this 15 may be comprising of 10s, 20s, 27s, 22s, consequently it may not be always 5. But if T A bar is lower than 20 significantly, maybe 15, 12, this is a very good calculation. You can check yourself, and with the data that is available in the sources that I mentioned, if as long as T A bar is less than 15, you can easily estimate the degree days within plus minus 5 degrees. Of course, if T A bar is 20, it does not mean it does not require heating. You may need both heating as well as cooling, okay, daytime cooling and nighttime heating. Then the domestic hot water requirement, this LDHW, mass of the water 500 liters, 200 liters or in kgs, multiplied by specific heat multiplied by TW minus Tm. This TW or the set temperature for delivery of hot water, and the Tm is the supply or the mains temperature. Now, we have to keep in mind the fact the best book, or rather a excellent textbook, is by Duffy and Beckman, and that is in the US. So, there is a supply or mains temperature, unlike what we have here is usually the ambient temperature only plus or minus few degrees, and this temperature is something like if you imagine you have a geyser and inside there will be a thermostat. It is set for 60 or 70 or 55, whatever it is. Many times we may not know it, but it is set for a certain temperature. So, it will cut off when the water inside the tank is heated. So, this in no way says that my solar energy system which is designed based upon the correlation of F chart, delivers at 60. What all we are doing is, if I store 500 liters of water with the conventional system to deliver at 60 degrees centigrade, when the means are being at a particular temperature 11 degrees C or 15 degrees C, whatever, then this is the quantity of joules we have to supply. So, consequently, this is the load on the system, but not a guarantee on the quality of the energy delivered, nor is expected. So, then L loss, lastly, UA of the tank, just like UA of the house, you can easily estimate for the UA of the tank. So, this is the set temperature. So, the tank will be basically inside at TW, losing heat to a temperature T surrounding. T surrounding, I have written it instead of the TA. The whole tank may be in a closed basement or inside your house. So, it may not be losing heat to the ambient. So, with this and this UA tank, one can estimate based upon the how much of insulation is there, what is the diameter, what is the free convective heat transfer coefficient, conduction resistance, and the area of the tank, or use from the manufacturer's specification. So, this total that should be only not L loss, it should be L equal to LSH plus LDHW plus L loss, where the three components are written as UAH into DD into 24 into 3600 plus MCP into TW minus TM and UA tank into TW minus T surrounding. So, now one will ask most important, because the other ranges of the parameters are given, flow rate and storage. These are the two variables. Flow rate can be changed if you want to improve the heat transfer characteristics. For example, instead of 10 liters you may use 15, though it may cost pressure drop may be more or it may go lower, or storage instead of 0.25 meter cube, and if it is a tropical climate, for the same energy or area of the collector you may provide 0.3, 0.35 or a larger storage. So, instead of another correlation for each flow rate, each storage, what they have done is, when the flow is non-standard, correct the variable as x c by x as actual flow rate by the standard flow rate to the power 0.28. Okay. If actual flow rate is let us say 15 and standard flow rate is 10, this is 1.5, 1.5 to the power 0.25 is more than 1. So, I will have a x c more than 1. It is little bit counterintuitive, but as I said, it is more to do with stratification. This is actual storage capacity upon standard storage capacity. I do not know, it almost looks like S and tan and dark flow rate. So, you can see that if actual storage capacity to the power minus 0.3, if this is more, this will be less than 1, making x c lower. If x c is lower, my F is higher. So, if the storage is more, my solar load fraction should be higher, which is borne by this particular relation. So, these are the correlation for the air based solar heating system, which can be expected to deliver energy at or about 20 degrees C. For an air based system, it will supply for domestic hot water or space heating, and combined domestic hot water system including space heating. So, we will go for the and the corrections for non-standard flow rate and non-standard storage have been given. Simply the coordinate x c is the corrected value if x is the one for the standard storage. This is how you modify. Now, you might wonder why x is changed and why not y. So, the answer is these are correlations. It is found that they actually correlate with the simulation results better, and consequently, x is corrected by this particular situation. Thank you.